1, 2, and 3. Double integrals in polar coordinates. Polar coordinates. So last time we left off thinking about polar coordinates as some sort of substitution like we did back in Calc 2, where we went from an x to a u as in a u substitution, or we went from x to a theta as in a trig substitution. And if you recall, in either of those substitutions, we went from a dx to something with a d theta, right? Or if we do a u substitution, we went from your dx to something with a du. But there's always this something here that we shouldn't neglect. And that something compensates for our transformation from one variable to the other. So what's happening here when we do a polar coordinate switch is that we're transforming our dA also known as dx dy or dy dx. We need to transform that into something that has a what? There's an r and a theta, so we need a dr d theta. And then the question is, what's going to go here? So for thinking about that, there's a nice nice geometric explanation in all the calculus textbooks that you have. So I'm not going to do it that way, because you can look at that and enjoy it. What I want to do is I want to take a look at this from a derivative point of view, where we're taking derivatives, because that's what essentially you're doing, right? Let's do a quick start of a trig substitution example back in Calc 2, where we have an integral that has a square root of 1 minus x squared dx or something. So you would do a trig substitution. You would say, oh, okay, I'm going to let x equal to sine theta, so that my square root will be 1 minus sine squared theta, which will become cosine squared theta, right? So I don't care about that stuff. What I care about is the dx replacement. And so what you would do is you would take the derivative of dx. So essentially you're just finding the differential. And so your dx is going to get replaced with not just d theta, but a cosine theta d theta. So what we have here is essentially the derivative of your transformation. And I'm starting to call this transformation. I don't know if you guys realize that. Because that's what's happening. In one dimension, we just call it a substitution. It seems pretty straightforward. It's just substitution. In two dimensions, this is also a substitution, but now they're calling it a transformation because it seems cooler to go from 2 dimensions to 2 dimensions. So what we're doing is we're going from the xy plane to the r theta plane. So what we need to do is we need to take a look at our relationship transformation, the functions that relate to x, y, and r theta, and somehow find a derivative of that. Now this is a little tricky because x is a function of r and theta, and y is a function of r and theta. So not only do we have two variables to replace, x and y, but they're going to get replaced by two variables, r and theta. So how many possible combinations of derivatives can you come up with this relationship? It's between 3 and 8. 4. So the correct answer is 4. So what are the possible derivatives? That's a silly question to ask, right? It looks like x, the derivative, x is a function of r and theta, so I can take the derivative of x with respect to r, and I can also take the derivative of x with respect to theta. And this is one of the notations. I suppose we should, maybe I'll use the other notation. That requires more writing strokes. But I think it's a little clearer. So x is a function of r and theta, so I can have x as a derivative of x with respect to theta and derivative of x with respect to r. And likewise, I can have the derivative of y with respect to r and theta as well. So I have 4 derivatives to work with, and somehow I want to try to combine this into one thing. So I can have this one thing to put with the dr d theta. And what do you suppose we should do? Whoever's taking linear algebra. It's even set up like a 4x4, a 2x2 matrix, right? So why don't we take the determinant of this? Wait, is that what we do? Yeah, sure. Let's take the determinant of this. What is the determinant of that? Well, let's figure out those partial derivatives first. The partial of x with respect to r is what? So cosine theta. The partial of x with respect to theta is what? And the partial of y with respect to r. And the partial of y with respect to theta. So let's take the determinant of that and see what we get. What do we get? R times cosine squared minus, there's a negative there, r times sine squared. So negative negative is a positive. We factor out an r. We get sine squared plus cosine squared, which is 1. So all we're left with is r. And that's your differential that comes out. So the reason why they don't do this at this point is because every time you do a polar coordinate, this is always going to be your derivative, because this is always going to be your transformation. So it's really not worth talking about this unless we really have to. And what happens in a lot of calculus textbooks is that they really just do the geometry of that transformation, and then they save this information about this special derivative. They save this information for the end of this chapter. So in section 1510, we'll see this pop up. Okay. So just to give this a name, this is called the Jacobian. Jacobian of the transformation. Yeah?
So, so we only use the determinant when we're trying to find max and min, so what does it actually do?
So the determinant for max and mins, when we do the second derivative test, deals with the second derivative. So that's a little bit different.
Right, so what is the determinant in general?
The determinant, I guess, for just to simplify the idea, the determinant is a way to collect pieces of information and try to make it compact into a scalar. So that's what we have. We have 4 pieces of information that are separate, but then we want a scalar out of that. So the determinant is one way to get a scalar from a matrix, right? I did the.
F of x times f y y.
That line that says R.
Oh, this is a. It's r cosine. Oh, I forgot the theta. It's r cosine theta minus negative r sine squared theta. And so that's there's the plus plus. Okay. The Jacobian is essentially the derivative of the transformation. And we'll talk more about transformations in the last section. But the main point is that our dA, whenever we switch to polar coordinates, our dA is going to become r dr d theta. So don't forget about the r. Okay? All right. So we kind of saw yesterday why it would be a good idea to try to do things in polar coordinates, and let's just do a couple more examples of why I think that would be important, and then let's pull some examples from the book, and then we'll there's this one cool piece of information fact also about that deals with statistics, a special function in statistics. So let's what are we going to do again? Oh, let's just do an example. So let's do like number 7. Let's start off with one of those types of examples. So, I realized, by the way, why they call it R in the beginning and then now they're starting to call it D. They call it R because all those examples were all rectangles. And the D is just the general area that's not a rectangle. I'd like to be able to call it R or D for any reason, as long as it's two-dimensional. So anyways, here's an example. Our integrand is x squared y dA, where D is the top half of a disk with center at the origin, and it has radius 5. So let's start off by drawing that region D. And just for fun, let's set it up as if we were going to do this in Cartesian coordinates first. Okay? So we have to decide what to integrate with respect to first. One is easier than the other, but since we're not going to do it, it doesn't matter. So what should we integrate with respect to first? Let's integrate with respect to y first. So if we integrate with respect to y first, I will draw a line parallel to the y-axis, and I will see where my line is going to enter and exit those the region. And it should be the same regardless of where I cut my region, right? So I have my limits of integration, I usually like to set it up like this to begin with. And then I ask myself, on that vertical line or line parallel to the y-axis, I enter my region where when y is equal to? When y is equal to 0. And I will be inside of the region and exit when what? Y is equal to what? So that circle, x squared plus y squared is equal to 5 squared, you have to be comfortable and proficient enough to be able to move that around and solve for x or y or whatever you need to solve for. In this case, it's the positive square root. It's the top half of the circle. And then you get 25 minus x squared. So that's your upper limit. Okay? And the x limits? Negative 5 to 5. So our integral then would look like this. We're going to integrate x squared y dA, but the dA is going to be changed into dy dx. Y is first, according to how we set it up. And our limits would go from 0 to square root of 25 minus x squared. And then dx, where x are constant limits to go from minus 5 to 5. Okay, so that's maybe not a bad integral, then you could probably do it, and then everything will still be okay. But let's redo the same problem. This time, putting it into polar coordinates. So if you're going to do polar coordinates, for the most part, we're going to be integrating with respect to r first. And theta will just be your angle that goes from somewhere to somewhere. So in this particular case, what is our r limits? Okay. So think about the polar coordinates as radial measurements going around at some angle. And so if you look at your radial measurement from 0, it's always going to have the same length regardless of what angle you're talking about. So it looks like we're going to go from 0 to 5, constant 0 to 5. And our angle goes from what to what? We have our convention of the positive x-axis being angle 0 and going in the counterclockwise direction is positive. So 0 to pi would be our limits. Now, having constant limits for both the inside and outside integrals is really, really easy. Not easy, but that's what we want to strive for. Okay? We want to try to push for constant limits, and sometimes you just can't get constant limits. And so for things that describe a polar function, especially circles, things that describe circles, our polar coordinate transformations will allow us to have simpler integrals, and if it is in fact coming from a circle, we will have constant limits, which is good. So I'm going to have constant limits, so I'll set up my double integral like this. Now, unfortunately, when I move from x, y to r theta, everything has to move from x, y to r theta. So our integrand will have to change. I can't just put x, y there. What am I going to have? R squared cosine squared theta for the x squared, and then the y is r sine theta. Okay? So that takes care of the integrand. Now our differential changes from dy dx to r dr d theta. Might sound funny, RDRR, but you always have to remember this. It's another common mistake that happens. Yeah?
If we're using that, then we're always going by R first?
Not necessarily, but like I said, about 95% of the time, the problems that you're going to be given, we'll integrate with respect to r first.
So if you did it the other way, would it just be r d theta?
Yeah. Because we have constant limits, you can switch the order of integration. It's not going to be a problem. There are going to be some times when you describe a polar coordinate that is not a circle, like one of those cardioids or leaf, rose leaf flower things. So those things are described by r that's not a constant. So r is equal to some 3 or sine 3 theta or something like that. So in those scenarios, we have to make sure you integrate with respect to r first. But in most cases, you can switch them around. Okay? So our r limits go from 0 to 5. Our theta limits go from 0 to pi. And so the integral is set up. Okay? There's another thing that they talked about that I didn't really discuss, but other things to exploit with double integrals is that if you can somehow separate, if you have factors of one variable and factors of another variable that you can separate by multiplication, then you can take advantage of that and do 2 single integrals. Okay? Let's see what I'm talking about. You guys are looking at me like, what are you talking about? So let's begin thinking about computing this integral, and I will start by simplifying the integrand. It looks like I have r squared, r, so that's r to the 4th, and then I have cosine squared theta sine theta. Now, if I decide I'm going to integrate with respect to r first, anything with a theta is constant, right? So I can take this cosine squared theta times sine theta and move it outside of the first integral because it's constant with respect to r. So then that will leave me with integral from 0 to pi, and the constant with respect to r, cosine squared theta sine theta. I can't take it all the way out because it's a theta, and the outer integral has a theta. 0 to 5 r to the 4th dr, and then d theta. Right? So I can, before I figure out what the integral from 0 to 5 r to the 4th dr is, I can look at this and say, well, if I do that integral, I'm just going to get a number. More importantly, I'm not going to get anything with a theta in there. So that's constant with respect to theta, so I could take that out. Right? So let's take that out. And so what do you have? You have the integral from 0 to 5 r to the 4th dr, and then the integral from 0 to pi cosine squared theta times sine theta d theta. And now I have 2 separate integrals, single integrals, that don't seem to be dependent on each other. And I can just compute one, compute the other, and then multiply. All right? So what I'd like you to be able to do is to go from here and say, hey, they're just products. They're just multiplied. I don't have an r plus theta anywhere. And look at the limits. They're constants, right? One doesn't depend on the other. So when you have a scenario like that, just look at this and gather all the r's together and integrate with respect to r, gather all the thetas together, integrate with respect to theta, and then that should be an easier integral to deal with. I'm still not going to do it because you guys can figure it out. But yeah, that's another one of the red boxes they have in the book, in the first section, the second section maybe. Okay. So is that good? These are easy integrals, right? All right. That's a good example. Let's see if we can find another one. Let's do one of these guys, the red one, number 25. Find the volume. Find the volume above the cone, square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared is equal to 1. So this is the old ice cream cone volume. So the important thing about this particular problem is finding the shadow on the xy plane. Sounds like a new concept, huh? Find the shadow on the xy plane. So instead of using this program, maybe I'll see if I can just draw it. Because if I'm drawing this, I'm looking at the whole sphere. And so what I want to do is I want to just focus on above the cone and below the sphere. So the sphere might go all the way around, but this is really what I want to look at. Right? So what I would be interested in, if I were to do this, if I were to think about this as a double integral problem, I want to know which one is my lower and upper surfaces so that I can subtract one from the other. And so I would probably want to rewrite this surface, these surfaces, as a z is equal to, well, the first one's already, the cone's already a z is equal to the square root of x squared plus y squared. But the sphere needs to be rewritten as a z is equal to something. So if this is the sphere and I just solve for z, and I know that I'm looking at the top part, I know I'm just going to look at the positive square root of 1 minus x squared minus y squared. Okay, so my inside of the integral will be the sphere minus the cone. Once you figured out which one's the greater function and which one's the lesser function, that's going to be your integrand. In fact, maybe we should write, just for practice sake, write our integral as the top function minus the bottom function dA. What am I missing? My d, right? What is my d? So my d has to be something on the xy plane that's going to be the domain of the difference between these two functions. So if I were to attempt to draw my domain somewhere, would my domain be that whole intersection where the sphere hits the plane? So it's really, what we want to think about it is, imagine that we trim this surface the way I have it drawn like this, and what we're looking at is the shadow that it has on the xy plane. So if we just focus on the shadow on the xy plane, if we can somehow figure out what that shadow is, then that's going to be our answer. And in this case, in fact, it's going to be the intersection between the cone and the sphere. Okay? When it's slanted, when there's like a plane involved that's slanted, then the intersection might be a little bit more difficult to describe. But in this case, it's just the intersection between those two things. So let's try to find that intersection. Let's intersect. Usually set some things equal to each other. Maybe we can set z equal to z and then somehow figure out what this is. I have x squared plus y squared plus z squared is equal to 1. And in place of z, I'm going to put in the cone function. So let's do that. And you'll see you'll have a couple of x squared plus y squareds that you can combine. So this is going to be x squared plus y squared. Both have a factor of 2 that you can bring to the other side. So you should get a circle of radius root 2 over 2. So that's your domain. Right? Any questions? I think I did it right. So this square and the square root would cancel each other. So we have a 2x squared plus 2y squared is equal to 1. And then I factor it out of 2 and divide by 2. And so I get x squared plus y squared is equal to 1/2. And now, having said that, I want to know what the radius of my circle is. So the radius is just, the square root of this thing. So that's good, yeah? I did everything right? All right, so now that I have my radius, I'm not going to bother trying to write this in Cartesian coordinate with Cartesian coordinate limits x and y. I'm just going to go straight into polar coordinates. So let's go straight into polar coordinates. And our r and theta, our r and theta, you think about the x and y being, square root of something minus x squared or whatever, some weird stuff. But if I would just want to describe the circle center of the origin with radius square root of 2 over 2 in terms of polar coordinates, what's my r limits going to be? 0 to the radius, root 2 over 2, and my theta? Looks like I went all the way to 2 pi. So that's my whole circle. Okay? Integrand will not be so bad. So we're used to looking at the polar coordinate transformation or the relationship between Cartesian and polar coordinates. Yeah. So we're used to looking at it like this, but remember there's another pair of equations that allow you to go backwards, back and forth here. So it's x squared plus y squared is equal to r squared, which you can rederive every time, but if you just remember x squared plus y squared is equal to r squared when you go to polar coordinates, then you don't have to rederive it. And then this is less important and less needed, but in case you might need it, the arctan of y over x is your angle. So with this in mind, or especially this, we can replace all the x squareds plus y squareds that we have there with r squareds. Right? So then let's go straight into our integral. Our integral is going to be the square root of 1 minus r squared if you factor out that negative sign. So negative 1 out here, and then you have x squared plus y squared. That turns into r squared. Minus square root of r squared. Well, let's just call that r. And that's our integrand. Right? Instead of putting in all those things, x squared plus y squared business. So yeah, so our dA, r dr d theta, and our r goes from 0 to root 2 over 2, and our theta goes from 0 to 2 pi. So you distribute the r squared, and then you would I'd probably want to split this up to two different integrals. Hold on. No, Brian, you going to say something?
Yeah, how did you get the square root of 1 minus r squared?
Oh, because I factor out.
Oh, there it is. Thank you.
Yeah. All right. So I have this thing. I guess I boxed it because I want it to be done. But before I be completely done, let's use that information about the different variables being factors, right? And then taking them out so that we have two integrals that we're dealing with. So how can we break this up to two separate integrals, single integrals? No, true. So this dr integral has no thetas at all. None in the limits, none in the integrand, none. Right? So you can move that, it's a constant with respect to theta, so you can move that out. So we can redo this as the integral from 0 to 2 pi of d theta. That's just going to be 2 pi times the rest of the integral that you might have to do a little bit of work on. Okay? So this is the same principle as the one we just talked about last time, when we got the thetas and the r's that we can separate as products, as factors, and then we can just separate the integrals that way. And this integral, if after you distribute the r, you would split this one up to two integrals, and then the first one will be just a simple u substitution because you got the r squared and the r would undo each other and they use substitution. And then the second integral will just be r squared. So that's r cubed over 3. And this would be theta from 0 to 2 pi, so that's just going to be 2 pi. Okay? So I think that's easy enough for you to handle, to do by hand. You don't need Wolfram alpha for this. I do, but you shouldn't. All right, is that cool? All right. Here's this problem that I sometimes give my Calc 2 students. It's been a long time since I taught Calc 2.
You love your answers so much.
Oh, by the way, I was telling somebody, I forgot who it was, but I have an integral worksheet. If you guys are interested, I can just, I'll post that online and you guys can have fun with integrals if you want. All right. Cylindrical drill with radius R1 is used to bore a hole through a center of the sphere, radius R2. Find the volume of the ring-shaped solid that remains. Express the volume, part A, in terms of the height of the ring. Maybe we'll just skip that. So this is an interesting problem. This whole idea about a sphere, and then you have a cylindrical drill that drills a hole. And I guess there should be assuming that it's drilling a hole through the sphere, so it's assuming that R1, the radius of the cylinder, is less than R2, the radius of the sphere. And they want to know about this volume that's left. Okay? So we probably want to set this up well, let's see. I want to try to identify functions here, functions that I can deal with. And I know this is a sphere, and I'll call the sphere x squared plus y squared plus z squared is equal to r2 squared. They want us to call that r2, the radius of the sphere. And so if I treat it, or if I want it as z is a function of x and y, then I would solve for z, and I would have the top half and the bottom half of that sphere. Now, since we're talking about volumes, and this is the top half and the bottom half, and they're all the same, I can just go from 0 to the top half and just multiply it by 2. Is that cool? So I'll say z is equal to the square root of r2 squared minus x squared minus y squared after you solve for z. And then I'll just consider the positive part, and then I'll say to myself, I'm going to multiply this by 2. So that's going to be my integrand, 2 times that. So now, the shadow. I want to see what the shadow looks like on the xy plane, because I want to set up my double integral. Yep. Okay. Way to steal my thunder. So I have the shadow of the sphere, at least, is this one big circle, radius R2, and then the drill has radius R1. And so there's going to be a space there. And so my domain, my D, is going to be this annulus. This washer. It's called an annulus. Yeah. Even looks like one. So I want to set up my polar coordinate limits. And this is where polar coordinates really comes in handy, because if I were to try to do this using Cartesian coordinates, it would be a big mess, because I would have to, split it in several things. And actually, what I could do is maybe I can even just, since there's all kinds of symmetry going on here, I can even just take a quarter of that and just remember to multiply this by 4. So let's let my D be this region in particular. Let's call this D prime. And then just remember to multiply by 4. So my R goes from what to what? So this is where it doesn't start from 0 anymore. It's going to start at some point. And whenever it starts at some point that's not 0, then you know there's going to be a space. There's a hole in this circle or some other graph, that whatever it is you're dealing with. And then the outer R, the upper limit for R is the bigger radius, which is R2. And then since we cut this into 4 pieces, we don't have to go from 0 to all the way to 2 pi. We just go from 0 to what? Pi over 2. All right. And we will integrate this. So we have a 2 from this 2, and then now as we set this up, we're going to have another 4 from the way we set up our limits. Our integrand is going to be R2 squared is a constant, and then x squared plus y squared becomes R squared. So it's a little tricky to read. Just remember that whenever you have a little r with a subscript, that's a constant, and the little r that doesn't have a subscript is your variable. And then a dA becomes r dr d theta, and this extra r, not only is it necessary, but it becomes really useful when we integrate, because now this becomes a simple u substitution instead of a more complicated trig substitution. And now our limits for r is going from r1 to r2. Our limits for theta goes from 0 to pi over 2. And we can play that same game where we can take out we can split this up to a theta integral and an r integral separately, because they don't seem to be combining. All right. So what could have been a difficult problem in Calc 2, where you have to find the limits of integration and stuff like that, has now become an easy integral for us. So if anybody's tutoring Calc 2 and one of your students come up with the same problem, then go through the pains and struggles to try to do it the old-fashioned way. Yeah. So let's call this an 8, and the theta gets taken out because it's constant, and then we have r1 to r2 square root of r2 squared minus r squared r dr. And this is a u substitution, and this is just pi over 2. Okay? All right, we should maybe take a peek at your homework and see if there's anything interesting there. In this section, right? What section is this? Ah. All right, so this is an interesting problem because this is not exactly the same kinds of circles that we've been dealing with. So this is a good problem to look at. I was going to see if I can find one like this, but Sergio found one for us. So we want a double integral of x dA, where D is a region, in the first quadrant that lies between these two circles. So the first circle looks like it's easy to deal with. I know what that is. The second circle, I don't know what that is. But if you think about it, x squared minus 2x plus y squared is equal to 0. And then you complete the square. X squared minus 2x plus 1. So plus 1 on the other side also. And then you when you finally complete the square, you see that the center point is not at 0, 0 anymore. The center point is somewhere else. It's at positive 1, 0. So your domain, or your D, you got a circle of radius 2. That's the first one. And then this circle is radius 1 with center point here. So D is the region in the first quadrant, so we cut this in the first quadrant and ignore everything else that lies between these two circles. So I'm thinking that it's this bit right here. Right? Between those two circles. Well, I don't know. If they wanted this one, then they wouldn't bother with the big circle because it's not touching the big circle. Oh, seriously, that was a good question. And so it should be the one that's touching both things. All right, so we want to go polar with this, and so we need the polar equations for these things. And I know I didn't really talk about this much, and I didn't really stress it much, but you need to know what this polar equation is for this function. I know that the polar equation for the outer one is just constant, which is the constant r is equal to 2. But can you take a stab at what the polar equation of that one might be? R equals something with a theta. You could. Okay, imagine this. When theta is equal to 0, I want to be at 2, right? When theta is equal to pi over 4, when theta is equal to pi over 2, I want to be at 0. When theta, is that helping? Yeah. So If you were to put sine theta, so these are, aside from the cardioids and stuff like that, these are the other common functions. If you were to put sine theta here, then it would be along the y-axis, smaller circle touches 0. But if you look at the different values for theta, you can kind of see how that is being drawn out. So let's put the cosine back, which is what we want. So this is how the function works. So what we'll use our cosine theta. R is equal to cosine theta for the other function. So now this is the case that we're not dealing with circles or washers now. Circles are centered at the origin and washers centered at the origin, but now we have a circle that's centered somewhere else. And so this is a function. R is a function. Now if I take a quick look at my R functions, my R, remember that your R is a radial distance from the origin out to whatever region you're describing. So let me draw a couple of rays. And if you look at the ray as starting from 0 and going off to somewhere else, I have this going from, it's kind of like that thing where you draw a line parallel to the y-axis and you see where you enter your region and exit your region, except my R is a radial distance from the origin. So if I draw a radial distance like this, I will enter my origin at what function? I'll enter my region at R, at the function R is equal to cosine theta. So that will end up being my lower limit. And then I will be in the region until I exit my region. And when I exit my region, what is my function there? R is a constant function too. So those will end up being my R limits. Is that cool? All right. Theta goes from where to where? Just goes from 0 to pi over 2. That's where it ends right here. Okay? So those are my limits. This is my x. Let us set up the integral. X is equal to r cosine theta. dA is r dr d theta. And my r limits go from cosine theta to 2. And my theta limits go from 0 to pi over 2. Can I split this up into an r integral and a theta integral? Why not? So because of that cosine theta and your limits, this r integral is dependent on cosine, not cosine, but it's dependent on theta. And because it's dependent on theta, I can't pull out that integral.
Is it just only this cosine theta or 2 cosine theta?
Oh. Yeah, there was a 2 there. Thank you. Okay. So if you have other weird things like the leaf, the 3-leaf rows, or the cardioids, or anything like that, where your r is a function of theta, you're not going to be able to split this up to 2 different integrals. Yes?
The radius of the smaller circle is smaller and not touching zero. We would be able to do it.
Yes, you would not be able to do it, because then it's not. Yeah, no, you can't do it.
You have to split it into 2, right?
Yeah, there has to be a way to somehow split it into 2 integrals. Okay. All right, let's, anything else? Okay, well, there's one more thing that I noticed in one of the problems we were looking at. And this is independent of being polar coordinates and stuff. And I'm going to leave this blank for a moment. But it turns out that we can use double integrals to find blank. Imagine that you're taking a double integral of 1. Let's say z is equal to 1. Can you picture z is equal to 1?
Yeah.
What is z is equal to 1? Tell me more. It's a plane. Not necessarily x equals 0. It's parallel to the xy axis and it 1 unit up. Okay? So this is a plane that's 1 unit up, parallel to the y-axis. So if I integrate a plane that's 1 unit up over some domain D, say the domain D could be a rectangle or circle or some other weird thing, and if I do this integral, what am I computing? I'm computing a volume, right? Double integral for us is a volume of something. So it's a volume, and then the integrand describes the height, and the d describes the base. So if your height is 1, what is this volume actually equal to? The area. So if you integrate a double integral where your integrand is just equal to 1, this is essentially the area of your domain D. So you can use double integrals. We're kind of used to having double integrals to find volume, but you can actually use double integrals to find areas if we let our integrand be equal to 1. And so in finding that area, you're really finding a volume. So technically your units are cubic meters or cubic length, but the numerical value that you get out of that is the same as the area, because it's just an area with height 1. Okay? So this is another interesting application for the double integrals. We think of double integrals as finding volumes of something, but you can also think of it as finding areas. Okay? And I don't know if I can do the next one in 3 minutes.
Can you still do it if the integrand is equal to another number? If z is equal to 3?
If z is equal to 3, then you'll have 3 times the area. But so it would still be a volume, yeah. But then you're saying that your height is bigger, and so you're not going to get exactly the area. Yeah.
Can you graph the first example?
What first example?
The very first. Yeah.
This one?
It's just after this week.
All right, so let's see if we can graph it. So if I were to graph this, I would need to take a look at my z is equal to x squared times y. And then if I want to look at my flat on the xy plane, so this is a little trickier. Top half of the disk. So radius 5. So I guess I don't have enough z. Oh, I probably need to go take this too. There you go. Something like that. So if I actually want to put a cover, I would put the cover on the outside of the cylinder. So if I can cylinder x squared plus y squared equals so it's inside of the half of this cylinder, I guess, and it would have to be a lot taller than this. I'll work on this and see if I can give you a nicer picture. All right, so now we really don't have time to do the last example, so maybe we'll start class with our special polar coordinate applications to statistics. See you guys tomorrow. Oh, quiz tomorrow. It's on what? No polar coordinates, just Cartesian.